my joint work with David Kazhdan and Edward Frankel. We have 3 papers on the archive. And this is dedicated to an analytic approach to the geometric Langlands correspondence. So I'm afraid I will not mention vertex algebras in this talk, although they are definitely behind, they're lurking behind this material. So let me just start, since I don't have very much time. So the setup is the following. So we start with a smooth projective irreducible curve over complex numbers. And then we fix on it n distinct marked points, T1 through Tn. And we consider the moduli space of stable quasi-parabolic PGL2 bundles of degree m on this curve. So instead of PGL2, we can take any semi-simple complex algebraic group, but I will, for simplicity, consider PGL2, especially because all the theorems that we actually proved are in this case. So a PGL2 bundle is the same thing as a rank 2 vector bundle or a GL2 bundle, modular tensoring with line bundles. And then I have to explain what it means stable and what it means quasi-parabolic. So, and actually I'm going to call them parabolic. The difference is small, so we'll call them parabolic. Parabolic means the following, that we have points, these marked points, T1, T2, and so on. And at each of these points, in the fiber of the bundle, fiber is a 2-dimensional space, right? Plane. And in the fiber, we are going to fix some line. It is shown here in green. So line through the origin, which is a point of the projectivization of the fiber, a point on P1. And that's called a parabolic structure at this point. Parabolic structure for the corresponding rank 2 vector bundle at this point. And so parabolic bundle is a bundle equipped with such parabolic structures at each of these parabolic points, T1 through Tn. So moduli space of bundles has dimension 3G minus 3. And then we fix n such parabolic structures. Each of them is chosen from a projective line. So the dimension of the resulting space is 3G minus 3 plus n, as indicated here. Now, the degree of a PGL2 bundle is actually not an integer, but an integer mod 2, because we can tensor with a line bundle, and that if we tensor with a line bundle of degree d, this degree changes by 2d. So m is going to be either 0 or 1. And finally, I have to explain what stable means, this letter S. So stable is traditionally defined in terms of slope of a bundle. So for ordinary bundles without parabolic structure, slope is equal to degree divided by rank. So in particular, slope of rank 2 vector bundle is 1/2 of its degree. But in the parabolic case, we are going to add, so this extension to the theory of stable bundles to parabolic case was developed by Seshadri. And the definition is that you add to it n over 4, where n is the number of parabolic points. So just a shift by some constant. But then also to define stability, we need to consider slope of line subbundles of E. And here it's going to depend on the kind of subbundles we have. Well, if there is no parabolic points, it should be degree of L divided by the rank of L, which is just degree of L, because it's a line bundle of rank 1. But in the parabolic case, we have to add something. And what do we add? Well, we are going to, so what does it mean that we have a line subbundle? This means that in every fiber, we have a line in the corresponding plane. So this is shown here, for example, in purple. And in some fibers over parabolic points, this line will coincide with the parabolic line. like here, for example, they coincide, but here they don't coincide. There are two different ones. And so we are going to count those parabolic points where these two lines coincide. And this will be called n sub L for a line subbundle L. And then the slope of L is the degree of L plus 1/2 of NL. So NL is the number of parabolic lines. And then stability is defined in the usual way. E is stable if for every line subbundle L, the slope of L is less than the slope of E. So, and one can show that, so bundles in general form a stack, which is a kind of complicated singular object, but stable bundles actually form an open substack there, which can be viewed as a smooth algebraic variety. And so quasi-projective, in fact. And so, so we have this variety, which is a union of two components, degree 0 bundles and degree 1 bundles. And what we, so analytic Langlands, so geometric Langlands correspondence is a theory which studies geometric objects on this variety, or more precisely on the whole stack, which are certain kinds of D modules and perverse sheaves, namely those which are automorphic or they're eigen sheaves of some Hecke function. But in number theoretic Langlands correspondence, in the usual one, what we study is functions on this thing, on this stack, namely on its points over finite field, which are eigenfunctions of Hecke operators. So in the first case, we have complex variety, but consider sheaves or D modules. In the second case, we have varieties over finite field and consider ordinary functions on the corresponding points. And analytic Langlands puts these two things together. So we consider functions, but on the complex variety. Or more generally, on the variety over a local field. And we want to do harmonic analysis on it. So more precisely, we want to consider L2 of this space, and we want to consider Hecke operators on it, and we want to study eigenfunctions of those operators. So, so while in the previous two versions of Langlands, namely finite field version and geometric version, it is important to consider the whole stack of bundles. For example, for number theoretic version, it's important because even very degenerate bundles, which are not stable, carry non-trivial weight or measure, and we cannot study L2 space without taking them into account. However, for if we're working over complex numbers and consider L2 functions, stable bundles actually form a kind of subset of full measure, because degenerate bundles form kind of set of measure 0. And so when you consider L2 functions, it's actually not important to consider degenerate bundles. You can restrict yourself to stable ones. And then it is very nice that this is a smooth manifold, and you can just consider L2 of the smooth manifold. Well, here I should make things more precise because, of course, to talk about L2 of a manifold, you need to introduce a measure on this manifold. And we don't want to do this because there is no natural measure on this manifold. But there is a way out, which is well known. Namely, we can mean by L2, instead of functions, we can mean half densities. So we take the square root of the absolute value of the canonical bundle of density, and look at sections of that. So in that case, if you have a section of that, then the squared absolute value of this section is a density, and we can naturally integrate it over the manifold without choosing any structure. So that's what I will mean by L2. And so I have a Hilbert space, which is L2 of Ban Sx, and it has two summons H0 and H1, which corresponds to different connected components of this map, corresponding to bundles of degree 0 and 1. So now I want to define Hecke operators, and this is for this so this is done by analogy with the case of finite field, and this is based on the notion of Hecke modification. So so let's say to define Hecke modification, we have a point x on our curve, which is not equal to any of the parabolic points tj. And then we define Hecke modification of a bundle E to define. Actually, I'm taking a stable bundle, but it doesn't matter in this case. You can do a Hecke modification of any bundle. And to do a Hecke modification, the data I need is I need to fix a line in the fiber EX of this bundle over the point X. In other words, a point in the projectivization of that fiber. It's a P1. And so then you can define a new bundle, which is HXS of E, which is defined as follows. It's a bundle whose sections are meromorphic sections of E with at most first order poles at X and no other singularities, and residue at the pole lying in S. Here I should say that, of course, we cannot define canonically a residue of a section of a bundle. Residue is only well defined for a differential, but up to scaling, this residue is defined by choosing a local coordinate, and the requirement that it belongs to S is scale invariant. So this condition makes perfect sense without making any choice. And also I should say that if we start with a stable bundle and do this transformation, then the result won't necessarily be stable, which creates a lot of difficulties in this theory, but generically it is. So it defines at least a birational transformation of some sort. Okay, and so now I want to explain what is Hecke operator. So let me just say what it is roughly, and then I will make things more precise. So, so Hecke operator is going to be an operator on this Hilbert space H, and initially it will be densely defined. So I will not be able to define it right away on all elements of the Hilbert space. I will define it on some dense subspace. And then the claim will be that it extends by continuity to the whole H. So the definition is very simple. Well, at first sight, namely, if I want to apply operator Hx, so Hecke operator depends on X, which is a point on the curve. And if I want to apply Hx to psi, which is a half density on the modular space, and evaluate the resulting expression on E, then this is just defined to be the integral or the average over all lines S in this projectivization of Ex, psi of the Hecke modifications of E with respect to ds, some measure on this. Well, so this formula, of course, raises lots of questions. One is an algebraic geometers question, which is, what is this measure ds? Okay, so of course, when we work over complex numbers over any local field, to define a measure on some variety, like in this case P1, we need to have a top differential form, and then we can take the absolute value of this form, or in this case, norm of ds is ds times ds bar in the complex case. But we need to have one form. And of course, there are many different one forms. It will be with poles, so there are many different ones. So which one do you take? Well, there is an answer to this question, which is contained in the work of Beilinson and Drinfeld on quantization of Hitchin system. It turns out, luckily, that there is a natural measure on this P1, which we can integrate against. And it precisely gives an operator from half densities to half densities. So I will not go into the details, but I want to mention that this is a new, so this is not very hard to prove, but the important thing is that this is a new feature of analytic theory, which is not really present in the finite field case, because in that case, we just sum over finitely many points, over q+1 points of this projective line over a finite field. So we do not need any measure. And also in the geometric theory, we don't have to consider that either. So this algebra geometrically, this works fine. But then there is also analyst's question, which is more difficult, and which is this integral convergent? So for which functions is this integral convergent? So you can show that it's convergent for some dense subspace of H, but then the question arises, is the result an L2 function? Why is it? And also, does this operator extend? Is it a bounded operator on the Hilbert space? And so these questions are hard and are open in general, but we were able to solve them in genus 0. So I will explain that in a second, but before this, are there any questions? Questions? Okay. So let me explain the answer. So there is a conjecture that these operators, in fact, do extend to bounded operators, and moreover, they extend to compact operators on the Hilbert space, which are also self-adjoint and pairwise commuting for different points x. So hx and hy commute. Hx, hy equals to 0. So I should mention that the non-trivial statement here that these operators are extend to bounded so first of all, I should say these operators are densely defined. So this is not very difficult to show. You can, if you take a function on bun, which is, so there is this notion of very stable bundle, which is a bundle which does not admit non-zero nilpotent Higgs fields. So it's a certain open set in the space of all stable bundles. And if you take a function which is compactly supported, let's say smooth and compactly supported on this set of very stable bundles, then it is easy to show that this integral will converge. And but it's not obvious that the result is in L2. So the conjecture is the result is in L2. And moreover, the operator extends to a bounded operator, and moreover, it extends to a compact operator. So those statements are non-trivial. Once you know that it does, it is easy to see that it is self-adjoint. It is simply because this Hecke modification, Hecke correspondence defining Hecke modification is symmetrical, and also pairwise commuting because Hecke modifications at different points are done independently. And also, after you know this, you can so there is this quantum Hitchin system, which lives on this moduli space. I will explain in a second what it is. And you can show that these Hecke operators commute with this quantum Hitchin system. So you might hope that eigenfunctions, they are going to have the same eigenfunctions. So let me just say a couple of words of what is quantum Hitchin system. So, so let me remind what is the usual Hitchin system. Let me do it in the case when we don't have any parabolic points. The case of parabolic points is similar. So we may consider cotangent bundles of the moduli space of bundles. And this is a space of pairs E phi, where E is a bundle and phi, so the cotangent vector is just one form on X with value in endomorphisms of E, which is called the Higgs field. Then this is a symplectic manifold. Well, of course, okay, so if you consider in general, it's a stack, but we can consider the stable part, for example, then it will be just a manifold. Then we also have this vector space, which is called the Hitchin base. And in our case of PGL2, this is just H0 of X with values in the square of the cotangent bundle, canonical bundle. So it is quadratic differentials, holomorphic quadratic differentials. And there is an integrable system, which is a Lagrangian map. So this has also dimension 3g minus 3. This has dimension 2, 3g minus 3. And so this there is a Lagrangian map. And this map is defined in a very simple way. It sends the pair E phi to the trace of phi squared. So phi is a one form with values in endomorphisms of E. So trace of phi squared is naturally a quadratic differential. And so this map indeed lands in this space. And in the case of parabolic points, we will one considers these Higgs fields with singularities. So it's very easy to generalize, and I will not explain this. And so this defines, if you think about function algebras, you get a map in the opposite direction from functions on this B, which is a polynomial algebra in 3g minus 3 variables, to functions on T star bond. And by the way, so this is all generators in this polynomial algebra are quadratic, so they have a degree 2 with respect to the phi. And so this is a commutative, maximum commutative subalgebra. And in fact, maximum Poisson commutative subalgebra, and this is called the Hitchin system. Now, Bellinson and Drinfeld proposed a way to quantize this integrable system. So in quantization, of course, T star of bond S should be replaced with differential operators on bond S. But it turns out that in order to get a quantization of this integrable system, you should take not the usual differential operators, but you should take so-called critically twisted ones, which means that they are twisted by they exactly operators that act on half forms. Act on the square root of the canonical bond of this plane. The way this system is constructed is the following. So you take, so this is a very rough, I mean, Bellinson and Drinfeld have a book about this, which is not published, which is long, and there are a lot of technology there. But very rough, at a very rough level, one can think about this construction as follows. You have the loop group G of T, then modular space of bundles can be thought of as a double quotient of this G of T, where G is, in our case, PGL2. Namely, if you have this algebraic curve, then you can think of, so there is a Drinfeld-Simpson theorem, which says that every G bundle on the punctured curve is trivial. And also, if you restrict the bundle to a formal neighborhood of a point, it also is going to be trivial. So we can think of the curve being covered by those two charts, the formal neighborhood of a point and the complement of the point. And then we have a clutching map, which is an element of the loop group. And then, of course, the two different clutching maps will define the same bundle if they are equivalent under right multiplication by Taylor series, which is a changing frame over the formal disk, and on the left by arithmetic subgroup, which is maps from X minus a point to our group G, and which is changing frame outside this. So modular space of bundles can be written as this double quotient, which is really kind of at the heart of geometric Langlands correspondence and in general geometric, well, and also usual one. So it's over function fields. So it's a fundamental fact in this theory. Then if you have a two-sided invariant differential operator on this on this loop group, then you can descend. This operator descends to the double quotient if it is two-sided invariant. But two-sided invariant differential operators are the same thing as the center of the enveloping algebra of the Lie algebra. Well, so center of enveloping algebra of the Lie algebra of loops doesn't have very interesting center. But if you take a critical central extension at the critical level, which is minus the dual Coxeter number for simple Lie algebra, then there is a big center and some completion. Namely, for GL2, this is level -2, and you just have Sugawara operators, which are quadratic expressions, which are second order operators. And so that's exactly what happens. So this is a twisted differential operator because it's at the non-zero level and exactly has the critical twisting. And when we descend it to the double quotient, we obtain a commuting family of operators here. Well, in general, we get infinitely many because we have infinitely many Sugawara operators Ti. But when we descend to this bond, only 3G minus 3 of them are independent and the rest expressed through them. So we obtain polynomial algebra inside here. And actually it turns out, as Bellinson and Greenfeld show, to be the entire algebra of differential operators on bond without singularities. And so this is called the quantum Hitchin system.
So, sorry, but this does not depend on X, on the curve?
Yes, it depends on the curve. So there is curve here, X. Everything depends on the curve, yes.
But you said this, what you obtain, the description you gave it's like the center at the critical level, and this does not depend on X.
That's right. This is a local system. So center exists in the enveloping algebra. It doesn't depend on X. And it is infinitely polynomials and infinitely many variables. But then when I descend those operators to this double quotient, well, there is a single quotient, which is affine Grassmannian, also doesn't depend on the curve. But the double quotient depends on the curve. And these operators become dependent there and form a system of transcendence degree 3G minus 3. And that's exactly this quantum Hitchin system, which depends on the curve.
Thank you.
Thank you.
Mm-hmm. And but it turns out that the spectrum of this algebra, commutative algebra, well, it's also a vector space, but it is not. Rather, it's an affine space. It doesn't have an origin. The underlying vector space is B, but this space is not naturally a vector space. It doesn't have an origin, a naturally defined origin, and this is the so-called space of opers. So that's basically. So it's a space of opers on X, and opers are, so I will explain what these opers are later, but in a moment maybe. So I said that these Hecke operators commute with these quantum Hitchin Hamiltonians, so those differential operators. And then, so if this first conjecture holds, this means that by the spectral, and we did prove that in genus 0, then, okay, so there is a very nice theorem in elementary functional analysis, which we all learn as undergraduates, and it is the spectral theorem of compact self-adjoint operators, proved by Hilbert, so Hilbert-Schmidt theorem. And it says that this family of operators admits a basis of eigenfunctions, psi lambda, so labeled by some discrete parameter lambda running through some countable set. And then hx psi lambda is equal to some eigenvalue beta lambda of x, which is a function of x times psi lambda. Here I should mention that this beta lambda, so I said that h was a function of x, but this is actually not quite so. H is a minus one, naturally minus one half density. So in order to define the actual operator normalization, you need to fix some coordinate. And if you, so this has to do with this measure that I skipped, didn't discuss. So naturally it turns out to be a minus one half density. So this is actually a minus one half density, not a function on x. And one question that we might ask, what are these eigenvalues? There are some functions on the curve, just real functions, because these are self-adjoint operators, and they're parameterized by some discrete parameter length. And here is the description of them. So here we should explain what those authors are. So, so author is a kind of an object which, in some sense, is a deformation of a quadratic differential. So, more precisely, it is the following thing. So, author, by definition, an PGL2 author is a differential operator acting from the bundle kx to the minus 1/2 to kx to the 3/2. Where kx is the canonical bundle. And it should have the following properties. First of all, it should have symbol d squared. And this condition turns out to be, so it's a second order operator, and this condition happens to be invariant under coordinate change. And because of the specific powers that we have here. And also, this operator needs to be formally self-adjoint, which again makes canonical sense because of these powers. So in local coordinates, it has the form of this Sturm-Liouville operator, d squared plus u. So this condition L star equal L just means that there is no mixed term, the first derivative term. So that's what an author is. And authors that appear here, so are so-called authors with real monodrome. So this is author whose monodrome. So author, well, for every author L, there is a differential equation L lambda beta equal to 0, and this equation is a second order equation on our surface. So it gives us a two-dimensional representation of the fundamental group. And author is called real if this representation can be conjugated into SL2R, or equivalently SU11, which is the same Lie group. And the theorem is that these lambdas are basically in, so for every lambda, there is a real SL2 author L lambda, such that eigenfunction, eigenvalue beta lambda of x is a solution of the joint system of equation L lambda beta equals to 0 and L lambda bar beta equals to 0. And so why does this does it happen in such a way? So because what do solutions of such a thing look like? Well, we have a basis of holomorphic solutions locally, which is F1 and F2. And solution of such joint system should be a combination, so sum of some products of holomorphic solutions by anti-holomorphic solutions. But this combination should be single value. And such combination exists exactly when monodromy lives here, because in that case, let's say, so we have a basis in which our Hermitian form is of the form Z1 times Z2 bar, plus Z2 times Z1 bar. And then we can consider, if in that basis we have basis of solutions F1, F2 holomorphic, then we can form a function beta, which is F1, F2 bar plus F2, F1 bar. And that would be a real analytic function, which is single valued. Single valued exactly because monodromy lives in SU11. And they will satisfy this equation and also complex conjugate equation L lambda bar of beta equals 0. So this is the picture. And Beilinson and Drinfeld tell us that if you have algebra A of quantum Hitchin system, then its spectrum is the set of authors, the space of authors. So this means that a quantum Hitchin system can be thought of as inclusion of polynomials on authors into differential operators, twisted differential operators. So for every author, we have a character of this algebra from A to C. And the proposition is that for every differential operator in this Hitchin algebra A, its action on the eigenfunction psi lambda is by eigenvalue. Eigenvalue is simply the character attached to this author, L lambda, evaluated at the element of A. And the d bar, the complex conjugate operator, acts by the same thing but complex conjugate. And there is also a conjecture that there is a simple spectrum. So eigenspaces are one-dimensional, and they are labeled by all real authors in a bijective map. And almost all these conjectures are proved for genus 0. I probably say a few words about that later. Also, I should mention that this is over complex numbers, but you could also solve this problem over real numbers. Then the answer will be a bit different, but there will be some geometry will be slightly different, and also you can do it over local fields. So if you take a Lie group G instead of PGL2, then of course these authors will be for the Langlands dual group, and this is why we call that Langlands correspondence. So this I said it was PGL2 authors. In fact, it's a mistake. I meant to say SL2 authors because SL2 is a dual group to PGL2. So so it makes sense over non-Archimedean local fields, but in this case we don't yet know precisely how to describe the spectrum, although it seems to have to do it seems to contain in itself the spectrum over finite field, the discrete spectrum over finite, which has to do with Galois representations. I should mention history. So this whole business goes back to the paper of Braverman and Kashdan in 2006, where they introduced these operators for non-Archimedean fields. Also, they were considered by Kontsevich in his paper on motives in positive characteristic in 2007. Also, Langlands wrote a paper in 2018 in Russian, where he proposed to consider eigenfunction. So consider he proposed to consider automorphic functions on moduli space of bundle over complex numbers, and proposed some method of doing that, but it doesn't quite work, but the idea is right. So it's essentially what we are doing. And then Teschner considered this spectral problem of finding single-valued eigenfunctions of Hitchin operators, which satisfy both Hitchin and complex conjugate of Hitchin system. In 2017, and actually in the simplest case, when our curve is P1 with 4 parabolic points, this was considered by Fritz Beukers in 2007. And there were also works of physicists. So, of course, Langlands, geometric Langlands was put in the framework of four-dimensional gauge theory by Kapustin and Witten. There were also important works of Nekrasov, Shatashvili, and others. And Gayota and Witten put in the framework of four-dimensional gauge theory this new analytic Langlands theory that over complex and real numbers, which we proposed in our papers based on these previous works. So that's kind of a bit of history. And so what I want to do now in the remaining time, which is, I guess, maybe 10 minutes or something, I should maybe describe what happens in some example. So any questions up to this point? So let me, don't worry, I'm not going to cover everything I just went through. So I want to explain an example. Let me explain. So the simplest interesting example is the curve, which is projective line with four parabolic points. So we have so this norm map on our local field, which for complex numbers is absolute value square, for real numbers it's absolute value, and for p-adic numbers it's the usual thing as well. And so I have if x equals to p1, and we have parabolic structure these 4 points. So generically, a vector bundle of, let's say, degree 0 has the form O plus O, so it's trivial. And so that means that the fibers at all points is a standard copy of two-dimensional space. And parabolic structures are therefore just points in P1, so complex number, or sorry, element of our ground field, or infinity. And so we have 4 points on P1, which are those 4 parabolic structures. And generically, one of them can be mapped to 0, the other to 1. Let's assume that all these things are defined over our field. In the complex case, it is, of course, automatic. So one of them can be mapped to 0, the other to 1, the third one to infinity, and then the fourth one will be whatever it is. So at 0, we will have 0, at 1, 1, at infinity, infinity, and at t, we're going to have what we have, which is y. And so this bundle is going to be called EY, and it is stable, one can show, if and only if y is different from any of those points, 0, 1, t, and infinity. And we also have, if you have a parabolic point, you can actually do Hecke modification at that point using the parabolic line as this S. And this gives you a birational, actually an isomorphism, not just birational, just an isomorphism between moduli space of degree 0 and degree 1 bundle. So we don't have to worry about degree by doing this identification. We will do this identification using the point infinity. And so then when we do Hecke modification of this bundle EY, at the XS, we obtain some bundle EZ. Well, we obtain a bundle of degree 1, but using this isomorphism, we identify it with degree 0, and then we get EZ. And the question is, how does Z express in terms of X, Y, and S? And the answer is that it's simply the following function. S minus 1 times st minus xy divided by s minus x, s minus y. And then we can compute this Hecke operator. And the precise formula for it turns out to be this. Hx psi of y equals to the integral over f of psi of s minus 1 ts minus xy divided by s minus x, s minus y. So this Hecke modification. And then comes this mysterious measure that I didn't explain, but in this case it evaluates to be ds divided by s minus x over times s minus y, norm of that. And so using this formula, we can, well, I mean, usually, so our moduli space of bundles is, in this case, coincides with the curve itself. That's a coincidence for this particular example, which is actually leads to a lot of beautiful symmetries, having to do with symmetries of Penn-Levy-6 equations. And so, well, integral operator should be written in terms of kernel, k of yz. And if we want to do so, we need to replace this thing by z. So make a change of variable. So go from S to Z. But note that this is a quadratic map. It's a degree 2 map from P1 to P1. So this means that we have a double cover. And when we change variables, we will get a factor of 2. And so the integration also will be carried over the image of this map. So if you are over non-algebraically closed fields, such as R or QP, we will only integrate over numbers which are of this form. And here is the corresponding. So if you make a change of variable, this will be just numbers which are squares. So the answer is the following, and this can be found in Pentsevich's paper. So we have this remarkable polynomial, ft of xyz, which is given by this formula here. And then hx psi of y is twice, so this is the 2 that I promised, the degree of the map, integration over f of square root of the norm of this polynomial, and times psi of z. And integration is only over points where this is a square. So this theta is an indicator. It's 0 if this is not square, and 1 if it is a square. So in particular, over complex numbers, when everything is a square, the formula is very simple. It is just this. And so if you look at this integral, let's say we look at this integral. So this polynomial f, if we look at this polynomial, we see it's quadratic with respect to each of the variables, x, y, and z. And it's so that means, so if we fix x and y, it's a quadratic polynomial in T, of course. Then it's quadratic polynomial in Z, and generically it has distinct roots. So if it has distinct roots, then this integral is convergent because it has 2 square root singularities, like this. But when the roots collide, what happens is you get, instead of 2 square root singularities, you have 1 singularity of the form 1 over x, which is not integrable. And so then you get logarithmic divergence. So looking at this kind of asymptotics, you see that you will get a logarithmic divergence. And so that will happen exactly at those points, 0, 1, t, and infinity. So this means that if we feed in a smooth function, we will not necessarily get a smooth function, but we may get functions with logarithmic singularity. But nevertheless, an L2 function. And in fact, you can show that this operator is compact just by direct computation. Then it is also self-adjoint. The corresponding operators commute. And the way it's shown that it is compact is that, well, what you do is, I mean, one way to show that an operator is compact is to show that it is Hilbert-Schmidt, which means its trace of its square is convergent. And well, that happens not to be the case here. The trace, and this is very easy to check using the Schwarz kernel. Namely, the Schwarz kernel should be in L2. So this integral should be fine. Well, that unfortunately doesn't hold for the kernel of this operator, but it holds for the square. And this means that the square is Hilbert-Schmidt. So this means that the square may not have a finite trace. In fact, it has a logarithmically divergent trace, but the fourth power has a convergent trace. And in fact, actually any power bigger than 2, like 2.1, has a convergent trace. So that's what happens. And maybe I should finish by explaining what happens with kitchen system here. So so in the Archimedean case, we also have these Hitchin operators. And in this case, it's just one second order operator, which happens to be this, which is the so-called Lamé operator. And it can be brought to the form if you, so there is this elliptic curve, y squared equals to x times x minus 1 times x minus t. And it's a double cover of P1 with Weierstrass points at 0, 1, t, and infinity, our 4 points. So if you lift it up, this operator to that curve, you will get operator of the form derivative with this is the coordinate, additive coordinate on the elliptic curve, plus 1/4 of the p function. So that's a specific instance of the Lamé equation with coupling parameter -1/2. And then, so it turns out that it commutes with this Hecke operator because we have this PDE for this kernel. And so the eigenfunctions of these Hecke operators satisfy this Lamé equation. So that's exactly the case which was studied by Bakers. So this lambda is called the accessory parameter. It's an eigenvalue of the Lamé operator. And the parameters that arise here are exactly those for which the monodromy of the Lamé equation lands in SL2R. Such parameters form a discrete family. And then eigenfunctions or NSU11. And then we make this holomorphic anti-holomorphic combination and we get a single valued eigenfunction. So maybe I should stop and maybe I should make some comments about this. So, so this is a story about critical level, but in principle it has a deformation to non-critical level, where instead of eigenfunctions of Hitchin operators, we should consider kind of solutions of so for example, if you have n points in P1, Hitchin operators are Godin operators, which are basically right-hand sides of Knizhnik-Zamolodchikov equation. But we can go off critical level, and then we will have actual Knizhnik-Zamolodchikov differential equations. And we have holomorphic solutions with which branch, which have monodromy, which is given by quantum group. But then in nice situations, we have conformal field theory, where we combine conformal blocks and their complex conjugate into combinations, which similar to this one, which give single-valued functions. And these are exactly the correlation functions of conformal field theory, not the conformal blocks, but the actual correlation functions that physicists are interested in. So this theory should be thought of as a limiting case of that when when level goes to critical, and also it's for non-compact Lie group. So this is the Zumina-Witten model of mappings not to a compact Lie group SU2, but to non-compact group SL2R. So this is a kind of Zumina-Witten theory for mappings of a circle into SL2R or Riemann surface into SL2R at critical level. This is how one should think. And moreover, it's not just chiral theory, but combined chiral, anti-chiral. So that's how one should think about this analytic Langlands over complex number. Thank you very much.
Okay, thank you very much. Are there questions or comments? Yeah.
Yes, so Sam has a question.
Yeah, maybe I should ask the question. So if G is a torus here, or say something like that, then the story is quite simple, right?
Yes.
Okay, so do you have a class of L2 functions in which you can control the Hecke operators? Say functions induced from a torus or something like this?
Well, I mean, no. What? No. So no. No, I don't know how to have a space of functions that is invariant. So there is a certain space which is called Schwarz space, and which is invariant under these Hecke operators, and which is like space of smooth functions, except that they are not really smooth. They have singularities along the wobbly divisor, which is the divisor of non-very stable bundles. But the singularities are not too bad. In this case, they are logarithmic, and if you have more than 4 points, functions are continuous, but not differentiable. So they have like power singularities, like square root of absolute value of x or something like this.
Okay, thank you.
Mm-hmm. Other questions? You're online? Okay. Okay. So how we do?
Yeah, just tell them to speak.
Please, Sam, please ask your question.
It sounds like you were just sort of addressing this, but I was just going to ask, so these eigenfunctions that you have, are they C infinity on the locus of very unstable bundles?
C infinity on very stable, yes.
They're
analytic, they're real analytic on very stable bundles. And over periodic numbers, they are smooth on very stable bundles. Smooth means locally constant. I'm not sure it is proved in full generality, but it's definitely, I mean, it's true in the cases that we've studied, like genus 0, and it should, maybe it's already, so Sasha Braverman works with Kazhdan on this, and I think, and with Sasha Polishuk, and I think they proved it in larger generality than that. There is no doubt that that's true. And it's definitely true in the Archimedean case, because these functions satisfy elliptic PDEs.
But on that locus?
On that locus, they satisfy. So the locus of very stable bundles is the locus where a quantum Hitchin system is elliptic. And therefore, by elliptic regularity, solutions are analytic.
But sorry, so there's, I mean, somehow for, well, I guess, so the question I had, I mean, I guess for the eigenfunctions for these, for these global differential operators, they should probably have wave front set and the nilpotent cone by similar reasoning. Is that?
Yes, exactly, yeah. The nilpotent cone is the, so the D module corresponding to this has a singular support contained in the nilpotent cone, probably the whole nilpotent cone.
Great, okay, thanks.
Okay, is there other question? So if not, we thank Pavel again. So we restart now. Is it correct?
Sure.
Sure.
I mean, unless
Okay.
Sam wants a
So
break.
Sam is the next speaker. So
Yeah.